Hello class, in this video we are going to be discussing how to solve for potential using spherical coordinates. And as we did in class, we will be using Laplace's equation. So in class we used a very simple case where we solved Laplace's equation for a cube given some initial conditions, and our equation turned into three derivatives, which in turn turned into three differential equations which can then be solved particularly easily. But there are some cases where we can't do it so easily, especially not in Cartesian coordinates, as so the example of a spherical shell. So now Laplace's equation becomes this big expression here, which can be found on page 141 of Griffiths, but we can see that our spherical shell has azimuthal symmetry, therefore we can get rid of phi in our expression and we're left with this equation here. And this equation is very hard to solve, therefore Griffiths has it in the book as a given, which we have here, which is a summation with two expressions multiplied by the Lagrange polynomial. And if you're curious, this derivation can be found on page 141 through 143. As an example, we are going to be solving problem 3.19 on page 149, where we have a spherical shell with the radius r, and the potential on this shell is equal to k cosine 3 theta on the surface and 0 everywhere else. And the problem states to find V in, V out, and the surface charge density, but given the time constraints, we'll be just finding V in. Given the general solution that Griffith gave to us, we will be finding V in using this expression, but if we look at the expression, this term in our summation, as we approach r is equal to 0 at the center of the sphere, will blow up to infinity because we have B over r, and this expression turns into 0 at the center, and so we get something that's undefined. Therefore we will omit this part of the expression and we get a new expression given here. So now what we could do is we set our expression above to our initial potential, but our initial potential lives at the surface of radius r, so that's why we need to plug in r wherever we have little r in our general expression, and we get this expression here. Since we are going to be using Lagrange polynomials to solve for this potential, let's rewrite 3 cosine theta in terms that makes it easier for us, and in doing so we get this expression here. We have to the third power, we have to the first power, and doing so we can rewrite it in terms of our polynomials, and we get k times some constant p3 plus some constant b p1, and we can expand this using the table of polynomials on page 142 in Griffiths, where p3 is equal to this expression and p1 is equal to this expression. And in doing so we have this algebraic expression here, where now we need to solve for a, and this is very easily done, where we can just combine like terms and we get such expression here, and now we just eyeball it. We get this equal to this, and in doing so we can solve for a here using some algebra, and we get a is equal to a over 5. Doing the same thing for b, we can find b using what we found for a, plugging in a, and we get b is equal to minus 3 over 5. Now that we found a and b, we can plug it back in to our initial potential expression using Lagrange polynomials, and we get this expression here. Now, instead of using Fourier's trick and having to do some nasty integrals, again, we can eyeball it as we did in class. And in class, we also learned that we only care about what's on the right-hand side. So since on the right-hand side, we only have P1 and P3, on the left-hand side of the summation, we'll be just using L1 and L3. Now, substituting what we found for V0 and using only L1 and L equal to 3, we have this expression here, and again eyeballing, we can find A1 and A3 very easily by doing some algebra, and we find that A1 is equal to minus 3k over 5r, where r is the radius of the shell, and A3 is equal to 8k over 5r, and we get the general expression for V in, which is this expression here. And we can also do this for V out, but we will now omit AL RL, because in Griffith, since v at infinity is equal to 0, this will not equal to 0 at infinity, it will blow up to infinity, and therefore to find v out we use this expression here. Thank you.